And we will actually do the alkene nomenclature, all of it later. That's like the next chapter is alkenes. That's it. You don't need to. And but just to practice a little bit. So I thought I'd give you some harder ones that the book gave you. So what we're going to do is we're going to assign priorities. Remember, we're trying to figure out the equivalent to cis and trans. Like this, what would you call this cis or trans? You can't, right? You've got all these kind of different groups on it. So it's hard to decide what's cis and what's trans. Same thing's true of this one. No way to really say whether it's cis or trans. This one's a bison. So anyways, we'll go from there. Remember the rule was atomic number. That's the first thing over here. Right. Second thing was we kind of draw a line like this. But I'll show you actually how you do this. Because if there's a tie, what you have to do is you have to look at the next atom out, next atoms out, and then list them according to their atomic numbers. And then, so that's what this little list is here. Go by atomic numbers first. If there's ties, you break it by looking at the next atom. Z is the atomic number. So I'm typing atomic number. And then you list the attached atoms according to their atomic number. And then the first difference is what breaks the tie. So if we look at this one on the left, and I'll kind of zoom in on that. This is a carbon, right? And this is a carbon. So that's a tie. That's what I mean. This atom and this atom are the same. So what you have to do is you have to list the atoms attached to that atom in order of atomic number. So if we take the top left, okay, so we're over here on this one. We're going to say this atom is connected to a carbon, and a hydrogen. This is, right? It doesn't matter which one you pick. So it's a carbon, this is the hydrogen. Down here, what's this?
Hydrogen.
It's hydrogen, right? And a carbon. So again, we're looking, the red one's the tie, right? The red underlined C is the tie, and then you look at the next one out. So this one has a carbon and then two hydrogens, so it would be C, H, and H. And again, this is in order of decreasing atomic, decreasing Z. And the Z is not for its decreasing atomic. So which one has higher priority? Well, this is a tie, right? This is where the tie is broken. So break the tie here. Because when you compare it to that, right, it's carbon versus hydrogen. Okay, so my high priority group is this one. This is 1, and this is 2. So do the one on the right. I have a carbon, right? So it helps if you underline it. So like this, and like this. And then list the things attached to that carbon, and then assign priority. When you do this, like, for a while, you just look at it and go, oh, that's it. You don't do all this ranking business, but you can look at it and just see, oh, that one's higher priority. But the first couple of times, you really should write it all out. All right, so, sorry, I did it already. It's BR, right? BR and H. And so that kind of already told us what it is. This is BR, H, and H. And so where does the tie get broken? On the second BR, right? So we're comparing those two. So this is 1 here, and this is 2. So this is Z. Which is why I put it under the Z side. Because originally it had it switched, and I thought, well, that'll be confusing after they go back and look at their notes because they forgot what I was talking about. Well, that's not Z. All right, I'll fix it. I'm rewriting these as we go along. I'm not even a chapter ahead of you guys. It's okay. I got this.
That's me.
I do this with every class all the time. But especially now that I'm writing on the screen like this, it makes a big difference how you lay the slides out. So I have to redo everything. I'm using a lot of the editor's material and stuff. I'm throwing it out actually, but taking their pictures. These are all ones they drew. So. Okay, so here it's easy, right? Because this is CL and BR, so which is higher priority? BR. Yeah. So this one we can decide already. This is 1. This is 2. The next one down, right, or the next side over here, this is carbon-carbon, right, here. So I would, again, highlight the one that's the tie, like this. Well, sorry, I meant to underline it. But there's no letter there, but that one and that one. So my list on the top one is carbon, carbon, and hydrogen. You have to remember there's a hydrogen here. And it's not often that matters, but it's important that you recognize that there is a hydrogen there. And this one is carbon and hydrogen and hydrogen. So the higher priority is this one here. Oops, that's a wrong green. It's that guy here. So my 1 is over here at the top. And so when you're looking at these two groups, there's a 1 here, right? There's a 1 down here. So this is E. Good? We'll move on from there. I don't actually know where I'm supposed to be in lecture right now. I guess I'm kind of on track.
On the test, is it 1 through 3 or 1 through 4? The chapter?
I forget.
One,
It
two,
says
three,
on there.
right? Because I thought since we're doing 4, you might put that on, but it says 1 through 3.
I'm pretty sure it's 1 through 3. You know I do that? Because I always fall behind at some
Yeah.
point, and I know it's lag the test. It also gives you more time. Okay, so now, now what we're going to talk about, so I skipped this slide, but you can do them and then come back to me later and tell me what you think, right? But here, you notice there's 2 cis-trans stereo centers. There's one that's here, right, and there's one that here. So you're going to have to make assignments for both of those. And then this one's easier because there's just the 2, but I'll let you guys do that and then come back and ask me questions. And this, do you guys know what that is?
What?
That's deuterium. So it's the isotope of hydrogen that has a neutron. So we give it a different letter in chemistry. We don't use the symbol H, but you have to realize that's a hydrogen with an extra neutron. If you have a hydrogen versus a deuterium, right? Deuterium's a higher. You can have hydrogen versus deuterium. It's not like good guys versus bad guys. It's not like Superman versus Batman.
They're both good. Yeah.
Okay, so chiral and achiral objects. So achiral objects are the same as their mirror image. Okay? So examples of chiral objects would be like your hands. If you took the mirror image of your hand, like it's easy to imagine the mirror image of your hand because you just do that. Right?
Uh-huh.
This is, and then that's the mirror image because there's a thumb here and a finger here, whatever it's called, middle finger, ring finger, pinky. What's index? And then if you go like this, you try to lay them on top of each other, they're opposites, right? So this is what we mean by chiral. The word chiral actually means handedness. So we have left hand. I teach kids this all the time. Left-handed, right-handed. Your ears are chiral. Like this picture of from the top of a car is chiral simply because you can't. The steering wheel is on one side of the car, right? Well, that's chirality. That's all that means. Achiral means it's superimposable on its mirror image. So like the simple fork that you could look at, or a chair that's symmetric, or even things like this. These are all achiral. They lack that feature which breaks the symmetry in their mirror image. So in fact, in chemistry terms, when you have chiral molecules, a molecule and its mirror image, so they're non-superimposable, those are different molecules. When it's achiral, and you take the mirror image of it and you build it, it's the same molecule. Okay? So what it does is it creates another class of stereoisomers that you need to understand because it's really important for a lot of things in biology and chemistry and that kind of stuff. So a chiral molecule has an asymmetric center. In carbon, the simplest way to do it is to have four different things attached. So this is not a molecule, it's a representation of a molecule, but I'm going to build it. Okay, I'm going to try to build it. I think I picked colors that I have.
I believe in you, Jay.
Huh?
I believe in you.
Yeah, well, good luck with that. I can't get a GC to go up run, so you know. Oh, I tell you, there's not enough time in the day for this class. I always tell people that organic chemistry is the best class to teach. It's the most fun. It's also the hardest class to teach. The preparation for the class for the instructor is crazy. But it's fun. Crazy fun.
I like my life. Never boring.
What an eventful day already.
Already event. You know those trees when you're driving and then you go to.
I know a lot of people that refuse to teach organic chemistry. They're like, nope, not doing it.
I live in Hartford.
I don't know why you
Obviously,
not
that's why.
do it.
It's so fun. You start work 5 minutes every day you got it. Brown state?
Oh, they use brown. Brown's not very pretty though, is it?
Every morning.
Oh, wait. So let's use yellow, but I only have one yellow, so I have to use orange. I could have done yellow if I had 2 yellow ones, but I don't have 2 yellow ones. Wait. What?
You use the white or the yellow.
I need a green and a red. Okay. I'll try to stick with the colors that are up there. So let's see, did I build this molecule? No, I built this molecule. No, let's see. Let's see. Oh yeah, I built 2 of the same ones. Right? Nice, right? So watch this. I'm going to make the mirror image. And this is how you actually do it on paper. I'm going to switch 2. It doesn't seem like that would do it. Like just switching 2 until you put it together in your head.
Look at that.
Oh, yeah.
See that? Red to blue, red to red, blue to blue, white to white, and the greens are on the outside. Now watch what happens when I try to make mirror. Ooh, they're mirror images. All right. So I'm going to switch 2. Doesn't matter which. It really helps to have a kit to do this. Okay. So now I'm going to try to make a mirror, see if these are mirror images. I'll do red. Nope. Let's try this way. There's blue, red, and green. There. Nope. Right? But look at this. I'm back to the same molecule.
Yeah.
So the simplest way to tell and create an asymmetric center in an atom is to create a point at which there are 4 groups attached. And it turns out like that sounds like, well, that's going to be hard. It's really simple actually, and it happens all the time. If I have this carbon, this one has the asterisk on it, right? It has a bromine attached to it, it's a CH3 attached to it, it has an H attached to it, and it has this ethyl group attached to it. So that is a chiral center. And if I built this, I could build 2 versions that are mirror images of each other. And then if I wanted to, if I built it and it wasn't the mirror image, I do exactly what I just did now. I just switch one of the sets of groups. Doesn't matter which. And you'll get the mirror image. So these are the same, right? So which ones do you want me to switch? I'll just do it one more time.
The white and the blue and white.
The black one.
The blue and the
Switch
white.
the black one. Huh?
The blue and the
The
white.
blue and the white. Like this one. Yeah. Blue and white. Not cool. I always thought that was fascinating, that you could do that and have it be true. But yeah, this would be a chiral center. And this is a stereo center, right? And for every stereo center that you can have a multiple of 2 molecules. So if I have one stereocenter, there's two molecules. If there's two stereocenters, there's actually 4 potential molecules that you can have because each one of them can be switched in opposite directions. And we're going to work on that, but I just wanted you to be aware of that. We're going to talk about one stereocenter for a while, then we'll move on to 2. Is this drawing style familiar enough to you guys? I don't have to explain too much. It's
I
the
like
range
it.
coming out,
Yeah.
that's the hatch going back.
The colors are, like, everything's
Cool.
great.
Good. All right, so which one could have or has an asymmetric center? And then identify.
Not the first one.
Not the first one, why not the first one? How do you know it right away?
Because you can't, you take out the OH, there's nothing on that, so they're not the same on each side. Like if you cut it in half, the OH is still there.
But you have to have 4 groups on it, right?
Yeah.
So if you look at this, this has 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, 3 hydrogens. So all of these carbons
There's, yeah.
have 2 of the same, so they're not
The same.
stereocenters. The middle one, here, carbon, right? You get to here, has a hydrogen, it has a propyl group, a hydroxy group, an alcohol functional group, and then a CH.
The third one.
Yeah, so it can't be at the end. That's kind of one of the rules.
Yeah.
If it's at the end over here, it can't be carbon. Oh, chain. But the best thing to do is just recognize it has 4 different groups on it. What about this one down here?
Yes.
Yes, no, yes?
Yes.
I get yeses and I
Yes.
get no's.
Yes. Yeah, because it goes C3, C2, CH, C2, C3.
So what's this? Ethyl. What's that?
That's what I
Ethyl.
said.
So it has, so it can't have,
Can't have.
yeah, it's achiral. So we would say the first one and the third one are achiral and this middle one is chiral.
C3, C2, CH, CH, C3.
Or has a stereocenter and can be
Because
chiral.
they can have 2 molecules in each stereocenter, right?
Yeah.
Thank you.
So the set of mirror images, right? These are the 2 stereoisomers of 2 bromobutane. I could build it, but I don't want to take so much time. But you get the idea. The mirror images are known as enantiomers. They're a pair. Enantiomers is a pair of molecules. This term that are mirror images and then we say they're non-superimposable. Jam it all in there.
Pair of what?
Molecules.
Oh.
Pair of molecules here that are mirror images and non-superimposable. If they're superimposable, if anything is superimposable, it's just the same. Okay? You can have 2 different molecules and they're superimposable. That just means they're the same molecules of the same substance. Okay, so enantiomers are different and they can usually be separated from each other. But here's the thing, their physical and chemical properties are exactly the same. So you can't separate them usually by distillation, and you can't separate them through like filtration or simple, there's chromatography, we'll talk about that more. They're hard to separate based on their physical and chemical properties. They'll look the same. They don't smell the same, actually, but they'll have exactly same boiling point, same density, same viscosity, all that will be the same. The way how do you think we separate enantiomers?
By smelling them? No, I'm just kidding.
No, you can actually smell them, and you're kind of separating with your nose, but you should smell things.
Remember when they used to waft it and they don't direct?
So
How do
if you,
distinguish that?
anybody here left-handed or you all right-handed?
I'm left-handed.
Wait, that's weird. You're right-handed? Okay, so if I were to put you all in a line, and you could stay in the class if you could shake my hand properly. Because in some countries, it's offensive to use
Yes,
the
if you
wrong
can,
hand.
yeah.
Yeah. So.
That's why I always shake with my right hand. Because I just assume most people are like right hand.
Yeah, I don't even, sometimes if I, person I don't know, I don't
I
offer
don't
to
even
shake
shake
until
hands
they put
anymore.
their hand up, because
That's true.
sometimes I don't even want to touch you.
No,
like-
I don't want to touch anyone's hands or germs.
I'm
just
okay
like,
with
"What's
that,
up,
but
buddy?"
so here's the deal. If you could only shake properly, right, and stay in the classroom, I would go through and shake all your hands until I got to these two in the front, and I would kick them out. Why would I do that?
Because we think we shake with our left
Because they
hand.
want to shake with their left hand, right? Well, they don't want to, but they that's the only hand, because they're left-handed, right? Why does, that would be a separation of chiral molecules. You could all be molecules, and all of you are right-handed,
I
except
feel
for these
attacked.
two that are left-handed. And the interaction that we have, based on chirality, based on our handedness, right, would cause those molecules to be separated out. And that's how it's done. You use a chiral substance to isolate chiral substances from each other. And typically, we do that using chromatography. The simplest chiral substrates are just made out of sugars, because the sugars are chiral. So if you take a sugar and you make you attach them to a surface, they'll have a chirality to them. And that chirality will help you to separate enantiomers from each other.
I have a question.
Yeah.
So would it be a different substance?
Yeah, it would have to usually be it's usually a different substance. Yeah, usually a different substance. But it just has to be chiral. Which, it's hard to make things like that in high quantities pure unless you have something that's already pure. And so we usually rely on a lot of these biological molecules that have chirality. That's how we originally synthesized chiral amino acids are chiral. And so you want to get the right-handedness of amino acids. They're synthesized using an enzyme, which is chiral, which will only interact with one-handedness of the molecule to produce the correct handedness. And then you'd have all this, half your molecules would be waste at that point because they wouldn't react. Anyways,
We're a waste.
was that?
We're a waste.
Yeah,
Thanks.
sorry, no problem. I could have had you be the only two in here, but I didn't want to upset the whole crowd.
It's because I can take it.
Yeah, I'm married to a left-hander, so it seems apparently we can all get along.
That's right.
So I've said a lot of this, right? Achiral molecules, mirror image is the same molecule, so they will be superimposable. Just some examples.
Superimposed are the same. They're the same.
Right, yeah. Superimposable is the same. So you can see these two molecules. This is achiral, but we drew it like it's a chiral center. But it has two hydrogens here, right? So you draw the mirror image, and then you can imagine to superimpose it, when you flip it over, you'll still have two hydrogens here. And so it'll be the same. Here, if we draw this molecule here, 2-bromobutane, right? And you have these like this. This is the mirror image. By the way, this is one of the ways you can draw the mirror image, is you can just draw it in reverse. Right? And that's how you draw one of the chiral, the enantiomer of that molecule. But you can see, hopefully, I don't know if you can. If you can't, I'll build it. You turn it like this, and where's this hydrogen going to be when I turn it?
Oh, in the front.
It'll be out in the front, so it'll be opposite this one, and they're not superimposable. Now, so one way to draw it is to do like they've done up here. What's the other way to draw it? This is an important skill for later. So let's say I wanted to draw, because I didn't have the image that's up there, I wanted to draw the enantiomer of that, and I didn't want to draw the mirror image because I don't like doing art. I'm just going to draw exactly the same molecule.
You just move them apart.
So the other way to do it, and I will draw it differently, but I don't attach things to it yet. Oh no, I didn't want to do that yet. Okay. And then what I do is I leave one of the groups in the same place, and I redraw it by switching two of the groups. And it doesn't matter which two groups you switch. Okay? So if I wanted to move the bromine down to here, that means either the CH3 or the H has to stay fixed. Right, well, since I put the bromine there, the H has to stay fixed, because that's where the CH3 was, right? I'll put the H down here again. I'll put the CH3 up here. Now, it doesn't look like the molecule over here, but it in fact is the same molecule. It's the mirror image just by switching to. You saw physically how when I switched two groups, I got the enantiomer automatically. What'll help you a lot here is building models and proving it to yourself with small molecules that, yeah, you can do this, right? So model kits are really useful for this whole section. Right. So just a little bit of terminology, because this will be confusing to students. This is an asymmetric center, right? These are also stereocenters. This is a cis-trans stereocenter. It's both of them together that make cis-trans. But here, right, it's the it's the chiral center. That's the same is true of here. These are potentially chiral centers here as well. Now, there's a reason why those are not chiral, and we'll talk about it later. But it has to do with its mirror image not actually being different. Okay. Oh, sorry. These are also, because of, this is cis-trans. Let me do that, cis-trans. But they're not chiral stereocenters. This is cis-trans. And this is chiral. What? You gotta get the paper off it. Are you eating cough drops?
Yeah.
It's an airborne. I feel like everyone's coughing around me, and I'm just like, does anyone want to get like the
But I
germs
can't
away
get
from
that
me?
paper
All right,
off.
so let's do this. Oh yeah, sorry. This is just examples. I think I have some others on a later slide. Right. If you want to draw, if you have perspective formulas, you can draw the mirror image. So that's what I did here. Right. And those would be enantiomers. This is a chiral center. This is in fact the same molecules before, but I just reoriented where the groups were. And then if you want to draw it in the same direction, now this is different than that one. This is a functional group, different number of carbons. But if you want to make the mirror image of this one, all you need to do is switch two groups. In this case, I kept the hydrogen the same, right? And I switched to CH3 and the OH group.
How do you know which one to switch to? So I thought
Just
you
depends on
switch-
what you want to see.
So can I switch to CH3 and the OH on the H?
Yeah, so I mean, you can play this game of, if I wanted to make that molecule, because that is the enantiomer of this molecule, right? You can switch this group and this group.
Okay.
Right? Or you can switch this group and this group, or this group and this group. If you switch this group and this group and this group and this group, guess what happened?
It's not the same.
You're back to the
Yeah,
original
it's-
molecule.
oh,
Just twisted it around in space. So that may not be apparently obvious. It's not to most people that you can just do that and that's the way it is. So you just have to remember until you get good at seeing them, right? So I'm going to teach you another way, Fischer projections.
Fischer.
Yeah, Fischer. Same guy who he discovered all the sugars. Like he discovered the structures for glucose and fructose. He did quite a bit of important work in determining what all the structures of the sugars are. Turns out a sugar like glucose has 4 stereocenters. He figured out the direction of every single pair of items on each on each chiral center. Okay, so the way we do a Fischer diagram is, I think of it as being like drawing them vertically, because normally we use these drawings for longer molecules, think of more than one stereo. Bless you. And we draw in this direction. So if you're looking at this, what this means is the CH3 and the CH2 CH3, so the methyl and the ethyl groups are away from you. Right? So I'm going to show you this. I'm not going to put all the hydrogens on. but I am going to attach the carbons and stuff. I could have left that one on. But I want brown. Brown is bromine, right? Sure. Okay. So that's this. That. Right. These are going towards you. There's my hydrogen, there's my bromine. This is a CH3 going back. And this is the ethyl group going down, away.
Oh.
So that is Fischer projections or Fischer diagrams, Fischer drawings. There's all kinds. Just if you see Fischer, that's so this is like this, right? So I think if you can't remember what it is, you can think of what a kid does when he sees his parent. They stick their arms out and they're like this. And their heads are back because they're running as fast as they can. I don't know. I just made that up. Well, I made
You
that
have
up
kids,
one time.
you know.
I got a lot of kids.
My daughter doesn't do that.
To
She
make
must not love me
the asymmetric center switch, right, like this, is to make the
It's like,
enantiomer.
I guess.
So these are kind of neat because if you want to draw the stereo center, it's real easy to draw it like vertically like this and then just switch the two groups on the side. That gives you the edge. You have to get good at all these.
I have to get good at a lot of things really fast, okay?
Yeah, I know. Okay, so now what we're going to do is we're going to assign priorities and we're going to assign a configuration to the stereo centers. That's what we're called. So I'm just going to show you. I already did it on here. This is O, so it's number 1 priority. This is a carbon attached to another carbon, so this is number 2 priority. Hydrogen always loses, no matter what. If you have hydrogen, it's number 4, so you can give it a 4 right away. You see it. And then CH3 is number 3. Okay. So now, imagine this is your car. Anybody here not drive? You. Okay, never mind. You don't count. So, is that bad? You're going like this. You're turning, you're driving in your car, that's your steering wheel. All right? 1, 2, 3. You go like this. Which way is the car going? Yeah. Knew that was coming. There's always somebody. This one's R.
It's usually the younger one.
It's kind of like, you know, your car, you're turning, that's what this is down here. Yes. I redrew it. It's turning to the right. That's where this arrow, that's what this arrow is. 1, 2. If you turn it the other way, now you notice this is the mirror image over here, right? On this side over here. But everything is opposite. If I do the same assignment of priorities, right? It goes like this. Oop, I want to do it in the just to see it. It goes like this. Oh, wrong. I need this one. It goes like that. So you're your car. This is a steering wheel column, by the way. The hydrogen's in the back, right? That's what the steering wheel has to be attached to something. Well, this is a really bad accident. It's not. But you're going like this, right? Which way are you turning? Left, yeah. Okay, now because of this, right? I'm driving at you, and I turn like this. Which way do you jump?
This way.
All right. You go that way, right? Even though I'm
Head
going
on.
left, you want to go that way to get out of my way, right?
This is the end.
So, but to you, when I do this, it looks like it's right. So you have to know which way the hydrogen is pointing. Like if you're seeing a car, if you see the driver, he goes like this. If you assume the driver is going the other way, and you decide to jump out of the way anyways, I don't know why you would just run away from me, you would jump in the wrong direction. Right? So you have to know. It wouldn't matter because they're driving away from you. But I can see May doing that.
I'll just go straight head on. That's it. This is the
Yeah,
end.
this is over. Oh, wait, they're getting farther away. Back up now. Oh, I guess I could be driving backwards. Never mind. Yeah, so the whole idea is the
See.
number 4 group has to be in the back in order for you to make this assignment. So if it's going clockwise or you're turning the car right, it's right. If it's going counterclockwise and you're turning your car left, it's L. So R and L stands for right.
He has a question.
Does it work out that 1 isn't right next to 2 and 4? That like 1
No, they always have to be next to each other. All right, 1, 2, 3, and 4, but they may not be in this order. So we'll have to come up with some rules for like when they're not like that. Because sometimes the 4 groups in the front, or it's on the side, or it's on the top, and then people get confused, like, well, how do I do the assignment? Because like, I have to look from, well, if you can look from underneath the car, you can do that kind of stuff. You could imagine yourself around the molecule and see it, which is what I do, but. But notice this one here, all right? This is one where the number 4 group is in the front. So when you draw the arrow, just ignore the number 4 group. And on your paper, you're just gonna draw something like this. Now that looks like it's going R, right? But here's the deal, all right? This is the column of the steering wheel. Should be on the other side. If I take this and I put it to the other side, you recognize that this arc is actually going, in terms of our perspective, it will be turning the other way. So right now, this is me driving at you. I'm going like this, right? Which way does it look like it's turning? If ignoring that I'm here, it's going like this. If this was your steering wheel, and you didn't have perspective on the 4 group, which way are you going? Going to the right. Because this is the way you turn your wheel when you turn to the right, right? I see Blake looks.
You're going
For you, it's left.
Huh?
For you, it's left.
Yeah, but like this, see if I turn it around, see what happens? So here, looks like that to you, right? It looks like that to you. This is the 4 group here, but you are in the front, right? You want it in the back. So it's actually going this way on the molecule. In order to get the assignment, correctly, we have to fix the position of the 4 group into the back of the molecule so that the steering column is always away from you in this sense. Right? So we're moving like, so right now this car is driving at you. The driver's gonna go like this, right? Which way are you gonna jump? You're gonna go that way, because the car's swerving this way, you gotta go that way, otherwise you just jump in front of the car, which probably happens about half the time. Mostly out of panic. Yeah, so, which way did you jump when you do that? To your left, right? So even though this looks like this, from the perspective of the driver, looks like the wheel is turning clockwise from your perspective, it's really not R. It's L because the steering wheel is actually flipped around. So what we typically say is that this one looks like it's R, looks R,
But it's
but it's S, right? Because the low priority group, the 4 group, is in front. And it needs to be in the back for the assignment of the configuration to make it unambiguous. And I don't have fantasies about running you over in my car and making you do chirality exercises.
oh no, we never think that, Dr.
Okay. So we're gonna have to do the same thing with Fischer diagrams.
I didn't finish the note.
Can you go back?
Is it L or is it S?
Huh? What?
It's S. Isn't it L? Because it's L because the
Yeah,
form
you
is
just use
S.
it. You just-
Look,
It
R.
looks like it's R, right?
It's S.
But it's actually S because when you flip this 4 group to the back, this arrow is pointing in the opposite direction.
Well,
Did I say something wrong on the slide?
Where did the S come
last line
from?
is L.
That was last time in L.
Oh, sorry.
I was wondering where the S came from.
Okay. Yeah. You know what it'll come up here. I'll tell you what it is. You know what S stands for?
No.
Stands for sinister, which is
Super.
left. No, sinister, which is left-handed
Sinister just sounds
in
evil.
Latin. Yeah, so that's where it popped out of my head.
You calling me evil? Thanks, Dr. I'm fine.
No,
No.
I'm not calling you evil.
I know the truth.
Oh, okay, I'm not calling you evil because of that. Okay.
Because of that.
So,
Got it.
Got it.
oh, sorry. Yeah, Fischer diagrams. So, you'll notice that the assigning of priorities 1, 2, 3, and 4, right? So we did that. And then you draw arrows 1, 2, 3 like this. So you have that arrow going like that. Which way is that hydrogen pointed? Front or back?
Back.
Back. So this one, right, designates as R. So remember, top and bottom are in the back. All right. This is in the back, so 1, 2, 3 going this way. And if it helps you, just draw the arrow to 1 and 2, and that usually is the easiest. And you just imagine the rest, right? This is going S. But the hydrogen's in the back, so it makes it easy for you to do that. Now the question is, what if it's not in the back? All right? So let's say it's in the, oh, you know what? I think I left something out. Hang on. Let me just see. Yeah, I want to show you one more example before I finish this Fischer stuff. I want to show you one more example here of doing the assignments when it's not clear. The way I've done it is it's in the front or it's in the back, so it's always easy to tell. What if it's on the top, right? So I'm going to draw a molecule like this. I'm going to draw the same one. And then I'm going to switch groups. Like that, okay? And I want to do the assignment. So I have to assign priorities to it. So you're still going to do that. So your priorities at the top, it's going to be 4 for hydrogen. This will be 1 for oxygen, this will be 2, and this will be 3. So now I have 1, 2, 3. Okay, I'll tell you how I do it. And then I'll show you a way to do it that makes it simple. Okay. But the way I do it is I just look at the molecule and I imagine the rotation going like this. Because this is the top. This is in the back, right? So go like this, and then I want to put the 4 group in the back. So actually, think about the rotation going this way, and then I put the 4 group in the back. That means the rotation goes this way. So that's S. Going to the left. Sinister. Okay, that's the way I do it, and you'll probably get to that point before too long where you can see that kind of rotational stuff. But you start here, you go to here, you go to here. You know this is on the side, that's to the back, the CH3 is to the front. So you're just following the tracing of where things are spatially, and then you just rotate it so the 4 group is in the back. So that means you're just going to tilt it like this, which means you just go like this. And that's what you get. The other way to do it is this: switch 2 groups, put the 4 group in the back. Okay, so we're going to switch 2 groups, and I'm going to go like this. I'm going to just say OH, C. Now I'm going to draw the same hatches and wedges like this, and then I'm going to put H back here, and I'm going to put CH2, CH3 here, and then I'll have CH3 here. Like the priorities are the same, so I'm going to say it's 1, right? This is 2, and this is 3, and so now it goes like this. So the wheel is kind of going like this, right? So that looks like it's R, right? how did I get that? Because didn't I just say this was S? It just said say it was S, right?
You switched them.
We said that one was S, the way I drew it.
You
And
switched
this one's
them.
R.
It's because you switched them.
It's because I switched one, so the original molecule was S. So what you do when you get stuck, you have a group in a position that you have a hard time visualizing, right? And this will happen. It happens to everyone. Right? What you do is you switch two of the groups so that instead of the 4 group being at the top, the 4 group is in the back. So wherever the number 4 group is, you shove it in the back, and you put the group that was back there where it was. You decide which way it's rotating, and it looks like it's R, which means the original molecule was S. Because I drew the enantiomer when I drew the second molecule. So what I did is I drew the enantiomer. By moving through, by moving, I feel like spelling cow, move, by moving the 4 group to the back. So if you know the configuration of the enantiomer, then the original molecule, you know its configuration as well. It's the opposite. Okay. Make sense? That's one of those techniques for doing these things that's, I think I forgot to put on my slides, but it's really useful in drawing the enantiomers. Okay. Let's see, did I do this one already? I don't know if I did, but in Fischer diagrams, you go to 1 to 2 all the time. Draw 1 to 2, right? And so it's going in this direction. So it looks like this is going to the right. Looks like it's R. But where's this? It's in the front, so it's S.
Holding.
Should have brought lab coat.
I
Melissa's
did,
got
forgot.
hers. You
I
can
know.
borrow hers.
Yeah.
So put it on there soon. Better take it down before she gets cold.
You're so fun.
I think there's one side.
I love this classroom.
It's only one side.
It's only one side?
One side.
He's only cold on one
Just
side.
Yeah. Oh, I see, yeah. You should get somebody to knit you a sweater with like a sleeve on this side and a short sleeve on this side. People are like, why do you wear that? Here, come to class with me, you'll find out. All right, again, so this one is in the front. So when you go 1, 2, 3, and it goes like this, it looks like it's S, right? But the 4, this is in the front. It's Fischer diagram. Side arms are front, and you want it to be always in the back, right? In order to have the configuration assigned correctly. You guys are funny. Okay, so one of the ways, and we'll practice more of these manipulations later, for sure.
That's your light bulb battery.
We'll move on.
That's what happens when I understand
So,
stuff.
plain polarized light. Oh, I meant to bring I have a whole set of polarizers. Plain polarized light. So you know what a polarizer is? Kind of? Who's had physics? Right. What is all right, awesome. So, that's usually how it is. So who wears polarized glasses? Right. Spend money.
Yeah, the transitions
Like
and all
these,
that.
when they darken, these are actually polarized.
Yeah.
So they're photochromic polarized glasses. Right?
Transitions.
Transitions, yeah, but they're actually polarized. So when you go outside, when you're looking, you're only seeing one polarization of light. Now, light is typically circularly polarized when it comes from, so from a light bulb, incandescent light bulb. So it's coming out of here, right? And waves of the light are going in all directions. So electromagnetic field are if you think about angles instead of like where the waves are going, when you think about angles, when it's traveling straight at you, you have a collimated beam of light, like this looks like this is a column. Then what happens is the waves are going like the electromagnetic field's going like this and like this, right? And like this, like this. And the physics people are going like this and this, I mean this, right? But that's okay, that's the idea. You get all degrees of polarization. Then when you put it through a polarizer, it filters out, it's a good polarizer, most of the light that's off polarization, that is, this is like, it's like it has a slit in it that only allows electromagnetic radiation of one angle to go through. So for this purpose, we're doing the vertical. So we put a polarizer. This is what your polarizers do in your glasses. That's how come when you look in polarized glasses and you look at a surface like water, the way they're set up is to block the light that is we call glare. Glare is the off polarization of light. And so that's why the glare goes away. And that's why you see, there's real polarized glasses are really dark because they're filtering out about half the light, just about.
The best kind of glasses.
They are good, no doubt. I really like them. Except, right, I wear glasses, so then it's kind of hard to get that. So then what happens is you can create an instrument. It's called a polarimeter, right? And you take a. This is just a setup for what's important. You take a glass tube. It's usually 10 centimeters long in the laboratory, but it can be different lengths. It can be longer or shorter. And the material will travel through the glass, the light will travel through the glass tube, and the glass tube has a solution in it, okay? If the material's achiral, the light goes straight through. So, in other words, right, an achiral compound doesn't affect this plane of rotation of the light like this. Now, put a chiral compound in there, and you put one enantiomer in it, not both. Just one of the enantiomers of a chiral compound. And what it will do is cause the plane of polarization to rotate as the light goes through. So it actually causes the electromagnetic wave to turn. Okay? If this tube is long enough, in principle, it can actually rotate it all the way around. 180 degrees, for sure, because after 180, it kind of just looks the same, because the wave's kind of like this. And when it's 180 degrees, it's still going like this, right? So you can't tell if it goes past 180, but yeah, you get more rotation of the light the longer this tube is. And so we use a fixed size. It's usually a 1 decimeter tube. A decimeter is 10 centimeters. Now, oh yeah. So how would you tell, like, that the light rotated, right? Because if you're looking at it, it's still to your eye, hits photons, hit receptors, your eyes are not polarized, says there's light, it doesn't help you at all. So what you do is you stick a second polarizer in the back. Oh, did I draw it? Oh yeah. This is it. You stick a second polarizer in the back, right? And you can use this polarizer to determine what the angle of rotation is for the light. And the angle of rotation, the alpha, the observed rotation, that's this guy here, depends on a couple of different things. But it depends on its, what is it called? I lost the word. Hang on. Maybe I didn't write it down here. Oh, specific rotation, that's it, yeah. I don't know why I couldn't remember that word. It depends on the specific rotation of the compound. That is, how much that compound intrinsically will turn light. Depends on the path length, and it depends on the concentration. Those are three things that it depends on. Right. So in practice, the way this is done is you take your polarimeter with nothing in it, okay? Or like an achiral compound or an empty cell, so there's no chiral compound in it. and then you take this polarizer and you take this polarizer and you set them at 90 degrees to each other. So think about this, light's going this way, right, through the first polarizer. If you turn the other polarizer from this angle to this angle, what happens to the light that tries to go through? It doesn't go through, it gets blocked completely. So if this had been vertical and this one had been vertical, then that light would have gone through. But if you turn it 90 degrees, because you've eliminated most of the light going in this direction, right? If you turn this to 90 degrees, there's no light that should get through. Because the first one blocks half of it, the second one blocks the second half. Okay, and then what you do is you put the compound in and then the light rotates. And then what you do is you turn this again until you get black again. And then you look at the angle that you've turned it, and that tells you how far the light has been rotated by the substance in the tube. Okay. Why did we do it that way? Just a general idea.
Science.
Okay, so let me give you, what's that?
I said science.
It's because of science, yeah. So when you go outside at night and you look up, what do you see?
Stars.
Yeah, when you go outside during the day and you look up, what do you see?
A big star.
Just one star, right? All the other stars are gone. What happened to all the other stars?
They went to sleep.
They exploded and then they come back. That's the way science works. No, it's just because you can't see them because it's a super bright background, right? They're there. Like think about that. The stars don't disappear. You just can't see them because everything else is too bright. So that's the same principle they're using in the polarizer. It's really easy to see a little light and blackness and make it completely black again. All right?
The sun is a bully. It's taking
So
over
what we're doing is we see a little bit of light when this happens, and we just turn it until it's dark again. And it's a much easier thing to see than to see when it's really bright again, because degrees of brightness, when they're really bright, your eye can't distinguish, but you know when you're in the dark, right? I mean, besides this class, you know when you're in the dark.
That's where I
On
live.
average, how long
In this
does
car. Yeah.
how long
I live in
does
this
it
car.
take to rotate?
Huh?
How long does it take to rotate? Like 90 degrees?
Oh, it's not how long, it depends on a
There's so
couple of
many lamps
things.
on, you don't
But
get
this
to
is
see
a
light.
specific rotation, right?
There's too many.
This is the observed rotation. I'll just tell you what these equations, this observed. And I've seen this done wrong way too many times. And I hope I'm not wrong, but I've seen it wrong so many times that I doubted that I knew how to do it. I went on the internet to just double check and get some examples, and I'm going like, that's not how you do it. That's not how you do it. That's not how you do it.
Maybe I'm wrong.
Yeah, that's it. I'm like, maybe I'm wrong. Maybe I learned this wrong. So I'll tell you, I'm going to tell you what the problem is. But this is the observed rotation. Okay. This is concentration. Now the concentration has specific units to it. This is in grams per milliliter or centimeter cubed. Okay. And this is path length. And like I said, usually this path length is 10 centimeters, but it's usually measured in decimeters. But a decimeter is 10 centimeters. Because I guess you could say a centimeter is a hundredth of a meter, a decimeter is a tenth of a meter, so there's 10 centimeters in a decimeter. And this is the specific rotation. It's very much like the specific heat equation, right? If this was Q and this was specific heat, and that was mass and change in temperature, that kind of thing. It's the same, that's why we call it specific. It's the amount of rotation you get for the path length and the concentration. Now, just a side note, okay. There are two versions of this equation, and I think that's where the problem comes from, actually. So this is the version that your book gives. This is the equation. I think they put D here. Just put C there, it doesn't matter. But you notice this is grams per centimeter cubed. So what is that a unit of? Density, right? So for pure liquid, it's the density of the liquid. So if you have a pure liquid and you're sticking it in here, the grams per centimeter cubed, that's the density of the liquid. So that's why sometimes you'll see D in there.
Because it's the density. Pure liquid.
So for a pure liquid, it'll be the density. And then the mistake that I typically see is if it's not a pure liquid, then we do concentration. And they say, this is what they'll say, it's the number of grams per 100 centimeters cubed.
Why?
I don't know. But it turns out, if it's grams per 100 centimeters, you have to put 100 up here in the equation. It's still just the concentration in grams per centimeter. But when they say, oh yeah, the concentration in grams per 100 centimeters cubed, this equation's not the right equation. There's 100 up in the top that cancels that factor out. I don't know why they do it that way. I would have just left it alone and said, good enough.
There's like three things harder than one.
What's that?
Are specific rotations okay?
Yeah, so specific rotations involve, actually do like the theoretical specific rotation. Apparently it's really hard. It involves quantum mechanics, the interaction of light with orbitals and all that kind of stuff. So yeah, my understanding is these specific rotations, like these numbers, are only determined experimentally.
So there's some guy in a lab who just like did this all his life, just like the material.
Yeah, they're called graduate students. And it's the lifetime of a graduate student, which is infinite.
Like me?
Because when one leaves, another one comes to take his place, right? And then they get knocked down. Okay, so that's the point I wanted to make, actually. So when you use this equation, don't be surprised if you're off by a factor of 100 based on book examples. In fact, I think the original example I used was from Bruce, and I'm like, that doesn't seem like it's right. So hopefully it gets changed in the future. Or at least they give the corrective factor. There's another equation. And I didn't read the book close enough, to be honest with you, to see if they gave both equations.
For pure solution, the concentration is the density.
Oh, let's see. I hope I did this right. Because I did use the book examples at one point. We'll just see if I did it right or not. So calculated the expected observed rotation of 2-butanol using a 10-centimeter cell. Okay, so what do we have? We have that the length is 1 decimeter. We have the density of butanol. I just looked that up, 0.805. And then I have alpha as the observed rotation, so I rearrange the equation like this, right? I plug in the specific rotation. This is the number that you would look up in a table. Now, this is some examples, but it wasn't on that table, so I just used this one instead. So I got 129, so you put 129 in here, you put the length in, and you take 0.85 as the concentration, you multiply all that out, you get 143. Okay. That makes sense? Pretty
You
straightforward.
just plug in everything and then you do the
Yeah,
problem.
know what the variables are, plug it in, and do the calculation.
Plug it
By the
in.
way, when we do the second exam, because this will be on the second exam,
I'm so excited.
you have to have a calculator.
Wait,
It's like the
Can I
only
use
test in
mine?
organic chemistry that you need a calculator for, except for in the lab.
Can I use my calculator?
You idiot, I don't care. Calculator. Okay, all right. 0.65 grams of cholesterol is dissolved in 15 milliliters of solvent using, because you're going to fill a 10 decimeter cell, so it has to have a fairly large volume. But it's using a 10 centimeter polarimeter tube, that's the cell. The observed rotation is 1.37. Calculate the specific rotation. So again, know the equation, but the specific rotation equation is this. I don't know if I did exactly the same way, but it's L times C. Maybe I gave it to you as L times C.
Yeah, you did.
Yeah, okay, let me switch those. I'll switch, because the way that I type stuff into the equation. So what I'm looking for is the specific rotation, right? That's this number here. So it's really just a plug and chug. You gotta put everything in. Now, the concentration, right? All you have to do is take 0.65 and divide it by 15. A lot of times when you're seeing these, you'll see that they say, oh, multiply it by 100 so that it's number of grams per 100 milliliters, right? That means the number will be 4.3 here. If you're going to do that, you have to take this and multiply it by 100. The equation's different, has a factor of 100. I've only seen it in one place, actually, where they say, yeah, be careful, there's these two equations, and you have to, that if you do it per 100, you have to multiply by 100. Okay. Anyways, L is 1. This rarely changes because that's just a standard size. And then, I mean, I could make it half of that, but that's usually kind of what it is. And then alpha is the observed rotation, right? That's just alpha. And then you plug that in here, and it's negative because I forgot to mention this. When you see the light, the rotation of the light, right? One enantiomer turns it to the right, and the other one turns it to the left. There's no correlation though between R and S and whether it rotates it right or left. If one is R and it's rotating it to the left, then its enantiomer will rotate it to the right the same amount. Which kind of makes sense in this weird symmetric way. Like if you have the opposite molecule, the light should rotate in the opposite direction. That's exactly what it is. Okay, so then you would just go ahead and do the calculation. You would get 32 as the specific rotation. Now, having said that, I didn't give a temperature or a wavelength of light, and I will make a note of that here. Yeah, cholesterol is 31 minus 31 and a half, so that would be it. Okay. So the thing I didn't say, a couple of things about this.
I have a question.
Yeah.
Can you explain again how you got the negative?
Oh, because when you're looking at it in the polarimeter and you want to make it dark again, you turn it to the left.
So are you basically
So-
just gonna always do the opposite?
Yeah, right-handed is positive, turning it right is
Of
positive,
course,
turning it left is
negative.
negative. Yeah. Yeah.
I don't know what's wrong
So if
with
the
it.
light is rotating clockwise and you have to turn it to the right to black it out, that's the plus. If it's going counterclockwise, you have to turn it left to black it out, then that's the negative.
I was like, what's wrong with it?
And like I said, if you have that, then you know the enantiomer of that molecule has to go the other way, because the mirror images rotate light the same magnitude, just opposite directions. Yeah, so a couple other things. These numbers all depend on temperature. It's not writing. Oh, there it goes. All depend on temperature and wavelength of light. So you always have to specify the wavelength. They've sort of standardized to 25 degrees Celsius, and a wavelength, and I don't even know the number, it's like 250 something, 253, but they'll put a letter D. And this is what is known as the D line of sodium. So if you do a line spectrum for sodium, it's been labeled the D line of sodium.
So it's a constant.
Yeah, it's a constant wavelength. So like if, I don't even know if we have polarimeter, I'm assuming we do, like every OChem lab should have one. I think they have,
Our
I
OChem
think
lab
they
is
have
lacking.
automatic ones. Anyways, yeah.
Does that say sodium?
It'll have a sodium lamp on it. So sodium lamp, if you're not familiar with sodium lamp, you remember the old street lights that were all yellow?
Yes.
Those are all sodium lamps. That's the lamp they're using. And they use a monochromator to isolate one wavelength. So monochromator just means one monochromator color. So it gets one wavelength of light. And then they use sodium lamp to generate that light. Oh, done.
Exactly, 10:45.
How much more do I have? Oh, gosh. I'm going to have to put more slides together. Yeah. What day is the test on next week?
13.
Thursday? Perfect. That gives me a couple more days to get the study guide up. I'll try to get it up tonight, and it might be by chapter. So I will try to break it up, and there'll just be questions, and I may or may not have answers. I don't know. Sorry. I'll try to have study guides with